All right. As people start filling in, I just want to remind everyone to turn off their cell phones if they have them on. And because this is probably going to be a packed session, if you have seats in the middle, can you scoot into the centers? Just as everyone is finishing getting a seat, we wanted to start off by playing a game. This is a demo that shows off some of the very cool things that I'll be talking about. But basically, you might recognize this as Quake, Quake 2. And the cool thing about this is that it is running exclusively with JIT compiled code. So it is the C++ program. And you can see that even though it's running with off of the JIT, it's still pretty fast and certainly playable. This is completely software rendering for graphics. There's no hardware acceleration. So even though we're dealing with a runtime that's got different performance characteristics, it's entirely a usable application. So not only is this a characteristic of C++, I was able to just take existing code for Quake and recompile it and run it off of the CLR. I'm also able to extend it with new features. And so one of the things that the designers of this game extension did was use the Windows Forms APIs and the drawing APIs to actually create a radar. So I could look around on the Quake map and see where enemies were, where some pickups were, and friends and those sort of things. So it's actually quite neat because all of this work is trivial to do. It was just some simple C++ code, building off of existing code, making use of new APIs. It wasn't a radical change in the program. It was very simple. And so with that, I just wanted to show you a very quick start as to what is capable with C++. And this is just the beginning. So with that, I want to thank Scott and introduce myself. I am not Herb Sutter. For all of you that know Herb Sutter, he was delayed over in the standards committee meetings for C++ in Hawaii, and unfortunately wasn't able to make it here. So I'm actually someone who works very closely with Herb on the C++ compiler and actually the language design. And so of all the people who could give this talk, fortunately I was here. My name is Brandon Bray. I'm the program manager for the Visual C++ compiler. And a lot of very cool things coming from C++. Some of the things I just want to make a note about with Quake is that while it was an existing code base and wasn't written to run with the CLR features, it only took them one day to even build it off of the CLR. And that's actually typical for I'm using a new architecture. C++ just gives you that ability. And all it took was actually taking C code and making sure it compiled as C++. That's actually not hard to do at all. And that was one day of effort. And just to create new extensions using new APIs from the frameworks was another 2 days. And put this together, we learned quite a bit. C++ is great because it leverages existing code. We think your code that you've written over the last 20 years is worth keeping around. It's what makes Windows and the entire software industry work. You guys did great stuff, and we want to make sure that you get to leverage that and make sure it's even better going forward. And so as we learned about this, what you see with our first attempt with managed extensions, we learned quite a bit. Managed extensions were hard to use. They didn't feel like a first-class language for writing CLR code. And in a lot of ways, people said, it's just not fun to write C++ this way. And decided to either ignore the CLR managed code entirely or switch to another language, and then they hit up problems because C++ has a lot of power, and those sort of things we miss when when we go to different places, because they tend to tame it down. So as we go, I think it's very exciting for our product group. We have such an opportunity to leverage the expertise of all of the C++ developers around here. So just a quick show of hands, how many people here actually like and use C++? That's great. I love all of you. So really, I want to say is that C++ developers are really the best programmers out there, and Microsoft recognizes that, and we want to make sure that we empower you to do your best. So everything about what we're doing in C++, we want to make sure that you get to do what you need, and there's just no limitation. There's no boundaries to your coding practices. You get to do what you want to do. And that said, I'm just going to go through the agenda. We have a very beginning of what led us to do what we're doing in this next release of Whidbey, and the rationale for that. We started a very scientific approach to this. Find out what C++ developers want, go talk to other people, and get people involved. We have a great community of C++ developers, and we want to make sure that all of you get the chance to say what you want out of C++ and that we give that to you. And following that, we'll just go through a very brief tour of the language. I'm certainly not going to sit here giving you a tutorial of how to program in C++. Most of it should feel very familiar to you, as we're just building off of existing techniques and just adding a few new features. And quite simply, the crux of this presentation really will be showing why is C++ great. Why would you want to use C++ in the future? It is a compelling language to use, and going forward, it's just one that I feel very excited about, and hopefully at the end you will also. And lastly, we'll talk about standardization efforts, because we know very well that C++ communities really enjoy having a standard with them. And that showed very well in our last release, where we focused entirely on building up our feature set to match what the standard required. And everyone really showed off and said, that's great, do more of that. So let's go ahead and talk about the rationale. Really, it started off with a concept. Everyone came up and told the C++ team that C++ really doesn't fit on the CLR. And how many people thought that here? And that's true. A lot of the things that we did in the managed extensions area felt very much like it was bolted on, or all we did was get C++ to work, and you had to use a bunch of these underscore keywords. So thankfully, we've heard the feedback quite loudly. Underscore keywords are gone from the language, and they're no longer to come back. So we're quite happy with that. The key question was that why would a C++ programmer want to use .NET? And the opposite also. And so those were the key driving questions for making sure what we did in the future. .NET has some extraordinary features that eventually C++ programmers would be remiss to live without. And garbage collection is very convenient. The security, built-in stack walking and making sure that you have secure APIs and partial trust, very useful. But C++ also has quite a bit of potential. It was missing features like templates for CLR types and deterministic cleanup. These are just things that you pretty much learn to use widely in C++, and because they were missing, it felt like all you did in the managed extension space was code C# code with a different syntax. And that's absolutely what we're trying to avoid in the future. There's different programming practices that C++ has that encourages better programming styles. And those styles are what we really want to bring to the CLR. So those were the driving factors. Let's just talk about how we developed this. We wanted to make sure that writing C++ code felt natural and that you got it right the first time. And verifiability happens to be one of the very important features on the CLR. It's one of those things that gives you the ability to have partial trust. And many of the new features coming up that you'll see, like click once, and working in mobile settings or off of stored procedures in the upcoming Yukon edition of SQL Server, really require some level of partial trust. So verifiability was one of those we wanted to give the compiler good diagnostics so you could write that kind of code, but also so that when you wrote code by hand, it just fell out naturally as verifiable code. There was no question. One of those things is we wanted you to be able to look at it and say, no, that's not verifiable because of this thing right here. And so here you'll see the most simple program, hello world. And this is actually a complete program. If you type that in and compile it, it will run and print hello world. So that's pretty obvious. It's not an unsafe program, and it will pass the verifier from the CLR. But we also wanted to make sure that everything that we did was a pure extension to C++. The key thing is that we want to leverage your existing code. We don't want to throw it out and say start over. No one I've ever talked to said that's a great option. It's one of those, we have customers that we talk to regularly that have code back 20 years from the DOS days, and they've been able to carry it forward into the current age. And it's really useful programs from some of our biggest ISVs. So that sort of thing, making sure that everything was a pure extension. How did we do that? We introduced new keywords, but most of them are context-sensitive keywords, so that you don't have clashes with other identifiers. And everything is quite elegant. You get to see a uniform structure to the language. Where something is garbage collected, you know that it's garbage collected, and you can garbage collect any type. So in the end, what we've done, and this is just the mantra that we've had for a couple years now, is we're bringing C++ to .NET. We want deterministic cleanup. We want, or deterministic finalization is something that you've heard we'll be talking about. We want templates. That's a huge modern C++ style of programming, and that works and will work very well going forward. And bringing .NET to C++. This is just one of those things. We have lots of features to bring, and every product cycle you'll see the CLR just increases in some kind of powerful way, such as right now they're introducing generics. Those things just come for free and for C++ if we just make sure that we integrate really well. So you'll see this in the slide deck quite often, where we have a cross sign. So we're really talking about cross products here. We want C++ and the CLR. We want all of the features to be first class, and then you can use them together. So you can use templates with reference classes, and you can use deterministic cleanup to create C# libraries. It's that kind of powerful approach that, just by combining features together, that makes you do the work that you can. So with that, we're going to start with the language tour, and quite simply, it's first, how do you write a class? That's where we start all the time. In the future, class still means what it's meant in C++. Struct still means what it meant in C++. If you want to write a reference class, one that will be seen as a class to C# or Visual Basic, you write ref class. And if you want a value class, you simply write value class. And interface class and enum class. And these are all adjectives to the word class. And so all of these are considered context-sensitive keywords. You can still use value as an identifier, which was very important to us, especially since almost every code base we looked at had that as an identifier. And going forward, you'll see, just as you've seen in other systems, int and the system int32 and the other fundamental or built-in types are exact equivalents. You might remember in the past that there were slight differences between them, and that is completely gone. They are exactly the same as you saw before. But the other thing, too, is that not only does every class, features that we've designed apply uniformly to every class. So every class can have a destructor. That wasn't true in the managed extensions language. And so I can write a destructor in a ref class, and I can write a destructor in a value class. And those destructors get called when I do delete, or when I have it embedded in another type, or if I allocate it on the stack. So that gives you the ability to say, I want a ref class allocated on the stack. And when it goes out of scope, its destructor is called. A finalizer is one of those where I get delayed opportunity. The garbage collector finishes, and I see that this object instance is no longer used, so run some code to clean up the resources it's holding on to. So a finalizer is something that I can put into any of these classes, including native C++ classes. So that definitely means that I can garbage collect a native class. So you can take your existing classes like a std vector or a std string and garbage collect those. Any type can have a copy constructor and an assignment operator, so they get all the C++ semantics that you know and can make use of. Any of these can be templated. So I can template a ref class or template a value class and create instantiations of them. So that means that I can use templates even for verifiable programs and still get completely useful languages. And I can even use templates in stored procedures for Yukon. I can even create a template instantiation and pass that off to another language for use. So I can create a specialized collection that another language can make use of. So we'll be talking certainly on these more as we go. Well, let's talk about properties. Really, when we looked at the past, properties felt very clunky. It didn't feel like a feature of the language so much as we got it in there somehow. So properties is what we looked at was, can we get an organic evolution of C++ to fully fit it in to the language? And so this born the concept of property blocks, and where you just declare a block where you declare the functions for get and set within it. So you might think this is similar to some other language that you might see, but not quite. What you're seeing here is the get and set are actually functions within that block. And so that gives you the ability to treat them and understand them as functions, because that's really what they are, and that's really how other languages actually see them. They throw the wool over your eyes in that case. But it still gives you the ability to do very cool things like bind a delegate to a function or a property setter, and so that you can see things changing even from anonymous code. We still give you we're giving you the ability to write an anonymous property, or a trivial property, sorry, where I just want to say this field should be a property because eventually I might do something custom with it. It gives you the ability to version between different binaries. And all that you have to do is write property in front of a field declaration. It's that simple. The compiler generates the appropriate get, set, and the backing store. So pretty cool, very easy to do, and a very natural way of introducing this. And what we're intending is properties would even be supported in native classes. And it could be even supported without the CLR switch. So it's just this natural ability to make use of features everywhere where it makes sense for you to use them. Index properties are an obvious feature, making a field look as if it were an indexed collection. And so in this case, you write property as you normally would, and you follow it with the bracket and the argument list. So these are the indexes to that property. You still get a get and a set as the two things. Another thing that you'll see here is that you can change the visibility of one of the get or sets by putting the visibility labels right in between your code as you would expect. And going afterwards, the default, we're allowing you to have default index properties, which we're missing in the last managed extensions. And these are the kinds of properties that C# and Visual Basic would recognize as indexers. But the default index property in this case is also public, protected, falls out of, stops when it goes out of scope. So you'll see that we have out-of-line definition for properties because they are actually functions. You're just looking at the scope. So I'm just looking at R, and lookup happens to be the name of the property and : : set. So you have a way to name that function when you need to refer to it outside of the scope of the property itself. And calling it is very natural. All you have to do is access it as if it were a field. And in this case, you could also access the object itself, similar to operator bracket bracket in standard C++. Delegates and events. These are key features on the CLR that actually give you the ability to write very simple code that's event-driven. We've seen very frequently that people like WinForms, and certainly many of you might see that the Avalon way of writing code where it's event-driven UI with very simple way of declaring it. It's very useful and actually reduces code size. So one of the things that we think is very important is that you have the ability to make use of that feature in your existing programs. So delegates and events happen to be what does this. Property, delegate, and event are all context-sensitive keywords. And so those are all things. Event happens to be widely used also, so that would be a bad word to reserve. And it's pretty obvious how you would use these as you'd expect. Delegate just goes in front of a function declaration, and it just defines a type that you would use in the event-driven world. One of the things that the C++ team is focusing on very heavily is making sure that MFC programs can make use of WinForms. And so we're developing those techniques and showing people how to make use of WinForms in their programs. And that just gives you the framework for how do I extend my existing programs to make use of them and of new features. And so you'll see that in other talks about how would I make use of the contact picker from WinFS in my current program. It's actually very simple, requires almost no code changes. So another thing that just shows kind of the power and depth that we have, one of the goals we had was there would be no language lower than C++ on the CLR. And to that extent, the design team has really taken that to heart. And that means we'd want to be even lower than IL in some cases. Just allow things that you can do at IL should be allowed in C++ as well. We give you the power to understand that. And so this happens to be one of those where we give you the full ability to override functions as you want. And so and a lot of the features that people have seen from experience in C#, we're also starting to bring that back to C++. So override and sealed are also context-sensitive keywords. And override says that I want to override another virtual function. FF in this case is not overriding another virtual function, as there is no FF in a base class to override. And so the compiler would issue a diagnostic there. If you didn't write override there, or you were overriding a virtual function implicitly, the compiler will give you the option to have warnings that you can turn on if you want to be notified of them. So you get the same productivity enhancements as you get from C#. So, but the key thing is that we're still giving that as an option to you. So it's a warning that we'll have off, and you're enabled to turn that on. Sealed is what you can use to make sure that that function is never overridden, and sealed can also be applied to a class to make sure that the class is never derived. And following that, you'll see a number of different ways to override individual functions. Even though x is overriding a function that's not named anything like x, I'm overriding, I1's g function. And that gives you the ability to provide private implementations for an interface, so you can call x through an interface and still get the same benefits. But I can also say, and for instance, z is overriding all instances of I, and there happens to be only one I. But if I had written h, it would find all of the instances of h in any of the base classes and override all of them. And this also gives you the ability you can do this in any kind of class, a reference class, a native class, that kind of ability. What we're doing is actually giving you access to the overriding semantics that the CLR has. And pretty much what we've done is said the CLR supports this. Let's make sure the C++ developer gets complete access to it. And that's what we've done. And the last thing that you'll see is abstract and new. Abstract is something, what you've seen as equals 0. We felt compelled to just give you a simpler and more elegant way of saying equals 0. And abstract is also a context-sensitive keyword. Equals 0 is also allowed to say that. Abstract is something you can apply to a class and even a native class, and sealed can also be applied to a native class. And those sort of things just, we wanted to make sure features are uniformly applied so that you only have to understand one concept. New is new. New says that I don't want to, you can use it for a virtual function or a non-virtual function, but I don't want to implicitly override a base class virtual function. And that's what that enables. So that covers the tour of the language. At this point, we're going to start digging even deeper into what some of these more interesting features offer and why C++ is great, because it really is. So let's just quickly talk about something that makes C++ C++. You learn this is that it doesn't matter how the type is defined. It matters how you instantiate the type. If I want it to be on the stack, I instantiate it on the stack. If I want it to be on the heap, I new it and create it on the heap. And so what we've done is say, well, you can continue to do that, and you can continue to do that with any type. And so that how you create the object is really what drives the ability to use that type. So if I want to create it on the native heap, I still use new to create it on the native heap. And that returns a pointer. And if I want to create it on the garbage collected heap, so in other words, I want to make sure that this type is garbage collected and cleaned up by the garbage collector, we use gcnew. And gcnew returns something new I will talk about on the next slide, but it's in short, it's a handle. We're introducing the declarator. What you'll see is either caret or hat. So I would read that as t hat t2 is a garbage collected instance of t. And you can still delete on those, which would call the destructor, and the garbage collector would just take care of cleaning up the memory, but you would avoid the finalization pressure by using delete on that. You can also declare it on the stack as you would expect by just declaring the variable, and its default constructor would be called. So why would you want to clean it or declare it on the stack is when it goes out of scope, its destructor gets called, so you get automatic resource management. And this is just something that we've built up a lot of expertise in the C++ community around. We have smart pointers and auto pointers, a number of other kinds of pointers that just help you make sure that you use resource management well. And so with that, we really wanted to make sure that kind of practice flows very well into the CLR space. And with that, let's just look at what pointers can do. Pointers in the managed extensions were very difficult to grok. We had at least 3 kinds of pointers, and knowing which kind of pointer you were dealing with by reading a line of code required something on the level of genius to figure out. And so we just wanted to remove that complexity from the language. Pointers never move. They point to something that's stable, and you can do arithmetic on them, comparisons, that, things that you would expect. And they refer to something that the user has to manage the lifetime for. So if I'm dealing with a pointer, someone owns the responsibility for cleaning up that object. And the other thing that we've introduced is something called a handle. And this is the caret. What it means is I'm referring to an object on the garbage collected heap. And that object, it is not my responsibility to clean it up or clean up the memory. And a hat has a number of restrictions that help you enforce that and make sure that you use it correctly and safely. So what it does is it does not allow you to take the, use arithmetic on it. This actually also allows us to do very cool things like user-defined operators. So a lot of the features that were sorely missing from managed extensions are enabled by just using a different declarator. Because it's got the caret, I also can make use of the CLR type system. So there is no void hat. Object hat is the definite or the ultimate base of objects. So there is still a way to make sure that you can acquire a pointer from something that's on the garbage collected heap. And that's still using the pinpointer abstraction, which the CLR exposes. What we do is we make sure that this is using the resource RAII approach to making sure that when I allocate or create a pinpointer, it's exception safe and does the right thing. And I can then use that to convert an instance over to a pointer. And the pinpointer still has the same semantics. It's mostly guided by the CLR, in that as long as the pinpointer is in existence, that object on the GC heap doesn't move. And so it is a valid pointer. It doesn't move. Once the pinpointer goes out of scope, that guarantee is lost, and pointer needs to not be used. So it still gives you the same ability to reason about your code. It's very similar to I declare a variable on the stack. I take its address. I know that I can only make use of that pointer while that variable is in scope. As soon as that function leaves, that local variable is gone. That pointer is invalid. I can't use it. So a lot of the reasoning that you get from using C++ still applies. References and this new thing called a tracking reference. Really, the problem with references, everyone pretty much gets introduced to the concept of a reference as it's kind of like a pointer, but the compiler dereferences it for you. So if you think about it, we'd still like to have references into the garbage collected heap. And with that, if I do that, I can't really use a pointer because the garbage collected heap moves memory around, and one of the fundamental reasonings about pointers is that it points to memory that doesn't move around. And so a tracking reference actually tracks things as it moves around. And so a percent is, kind of like a handle, but, the compiler takes care of, doing the reference stuff. And so what you'll see is if you want to use something like the ref keywords from C#, you would just use percent and reason about it in the same way that you would take the ampersand in C++. So when I call swap, I only need to pass the two arguments. I don't need to take the address of them and pass pointers or anything like that. And so what we also do is make sure that this continues to make sense. Ampersand, when I use that as a unary operator on an instance, that returns a pointer. And so a percent, if I use that on an instance, will return a handle. So for anything that I have, if I can always get a pointer to it, or I can always get a handle to it. And the type system, we've worked really hard to make sure that that works out. And as you write code, that's what happens, and it makes sense. So how do we accomplish this? It's certainly not true that I can just put a native class on the garbage collected heap and expect that to work, because as I said before, the garbage collected heap moves around, and native classes have something called the this pointer, which a lot of code expects to stay the same. It doesn't move. And so doing this, a lot of the things that we're doing is really helping developers write the code that they're already writing, and just having the compiler do it by default. So we start off by saying that we are going to create a proxy. If you GC new a native type, we just create this very small proxy, and that proxy is responsible for managing the lifetime of n. So as long as I refer to that proxy, n is going to stick around. And once I lose all of my references to it, that proxy is going to be garbage collected, and its finalizer is going to clean up n. If n had a finalizer, this would be an opportunity for the proxy to call that finalizer. And so it fits very well together that it falls out from that design that we're just making use of the types. And so also, how do I create any reference type and make it appear that it has a stable pointer address? We create a proxy on the native heap. And it's the responsibility of the user to then clean up that memory. So if I knew this, that proxy is holding on to the R. If I lose all of my references or all the pointers to the R proxy, I will eventually leak memory on the garbage collected heap. And this is a concept familiar to C++ programmers, leaking memory, unfortunately. But very simply, all you have to do is call delete on our proxy, and it will release all the references. It'll call the destructor on R, and because R won't need to be finalized, R then just gets its memory cleaned up. So it just falls out very naturally from that. And we'll build on this as we go through the slide deck to see some of the more interesting and very cool features that fall out. So a ref class on the stack, pretty much what we're doing is the ref class actually can't be on the stack. That's a CLR requirement that it's on the garbage collected heap. But really, when we look at it, why do we put classes on the stack these days? It's not because we're trying to make a more efficient use of the hardware architecture. We're really doing it for semantics. We see this in MFC where you're allocating device context. And the right approach is to allocate it on the stack, because what you want is to free the resource when you go out of scope. You're only intending to make use of it for a short period of time. You just want some cleanup done, and you don't want to have to write that code. And so allocating those device contexts on the heap make no sense. In this world, giving you that ability to get the compiler to generate those semantics where the compiler generates the cleanup code, because it's pretty obvious code, it's really easy. So that's what we're doing. The compiler sees that you wanted it to have stack-based semantics, so lexical scoping. And when it goes out of scope, do something. And so going out of scope, the compiler just generates the call to the destructor, and the destructor gets called. That R is never finalized, and the world's great. So I certainly will talk more about this as we go forward, just how well we can make use of the deterministic cleanup that gives us. So boxing is something that's new. In the managed extensions, we had this __ box keyword. And a lot of people said this was great because now I know when boxing is going to occur. And about a week into coding with managed extensions, everyone came to us and said, gosh, I get this compiler error saying that I needed to box here. Why can't the compiler box for me? So really, that's what we've done. Implicit or boxing is great. It does have a slight performance cost, but when you need it, you really can't avoid it. It's just something that was designed into the API. So when you called system console writeLine, you really needed to have boxing there because there was no alternative. And this gives you that ability, and it fits into the type system really well. If you want a boxed instance of a value class, what tells you that it's on the garbage collected heap? It's the handle. So if I want a boxed instance, all I have to do is put a caret after the value type name, and that tells you it's on the heap. Just as if I put a value class on the stack, I have no declarator following it. And so it makes a lot of sense. It fits into your knowledge. What this does is actually just give you a transition, a conversion between something that's on the stack or embedded in a class, and it can be put onto the garbage collected heap as a copy. And so what we do is actually tie this into the notion of a copy constructor. We're just saying that in some instances, the copy constructor for a value class is called implicitly. Unboxing is also explicit, as you would expect. So we actually are supporting the notion of strongly boxed types. So it's not a conversion from int to object hat. It is a conversion to int hat. And int hat is a distinct type from float hat or any of the other box types. So they're strongly typed. You don't have to rely on dynamically testing, is this an integer, when you're trying to unbox it. So if I have a strongly boxed type, all I have to do is use the star to dereference it. And so a star is used to dereference both handles and pointers. That happens to be one of the things that, as I'll talk further, we've been consulting a lot of the C++ community. Why is it star and not hat? That's when we asked Bjarne Strustrup his opinion, and that's what he wanted. So we've been working with them. But the other thing is that the cast notation you can cast directly from an object hat or an interface hat. And they work together to go directly from those to the value type, and the value type is copied as you'd expect. So a lot of very things here. Explicit boxing is really easy for the compiler to do, but explicit boxing is really annoying to the user. Implicit boxing has a lot of things for the compiler to figure out, and so we've spent a lot of time making sure that it's done right so that the user experience for C++ is really simple. It just works as you'd expect. So as an aside, that gives all of this algebra that we've developed for pointers and handles gives you the ability to write some very cool templates that work on pretty much any code. So in this case, if I want to write a swap, I can just use %, and that handles garbage collectedness just as well as it handles anything that's on the native heap or on the stack. And putting that together is pretty cool because all the things that are allowed by it, everything can compile. I can use this one very generalized function, which is pretty much the goal of every C++ developer, is make use of this very advanced feature so I only have to write it once, and don't make me write it 50 times. So making use of that experience gives you the ability to write templates that work on anything. And with that, we have the much-awaited feature, deterministic finalization. So we've heard from pretty much everyone that just as much as they like C#, they really want deterministic finalization. And so what C++ has done is just give you real destructors. You understand destructors, and that's how they work. And really what we look at is that over the last 2 or 3 years, using code on the CLR, you're trying to avoid finalization by doing cleanup early. So we've built this pattern around it. It's a dispose pattern that I make sure I implement this interface. I call the other dispose methods in my base classes and the classes that I'm holding on to, and that I get some good language support for calling dispose when I needed to. And as far as C++ goes, normally the evolution of a language is to start off with a pattern and then add full language support for it. So really we were a bit confused with this. This seemed like a regression. As far as deterministic cleanup is something that's really well understood. And why it was missing, it just made us feel like, great, we can do what people already understand. And so what you'll see is what C++ does is just use destructors to implement the dispose pattern. So when you're writing C++, you never have to write dispose or call dispose. It's just done for you. So just as a destructor calls its base destructors, and it also calls the destructors for elements embedded within that class, that gets codified. The compiler does all of that for you, and it'll do that for the dispose patterns too. So when you write a destructor in C++, another language will see it as dispose, and they'll have to use using and call dispose. When you allocate something on the stack, because dispose is the destructor for C++, the dispose method gets called when it goes out of the lexical scope. So all of this happens for you automatically, and it really helps because when we look at code that has a lot of try finally and things like that, it tends to get rather fragile. As projects grow in size, we see that, oh, I forgot to call, put a try finally around that call, so I leaked something. So how many of you were here for the keynote yesterday where there was a dangling port that was left open when the application crashed? And that sort of thing just shows that they forgot to make sure that in an exception-safe way during a shutdown that ports were closed. And so when you're using patterns that the compiler helps you create, you avoid those issues entirely. And so the C++ offering here is that, really C++ is offering a way to write more reliable code. The notion that C++ is dangerous because it's got pointers is really unfounded now. It actually can help you write bigger programs that perform better and have fewer errors. And so really, I think one of the key things that we wanted to get out is that having to write try finally in code is something that we want to avoid. It's better style to just write something that's exception safe via destructors and we're giving that to you via every class type in the system, and that gets exposed to other languages as you would hope it would be, and as disposed in the patterns that they can use. So you can actually write really robust libraries in C++ that other CLS languages can make use of. So really, I think the point that was at the bottom is that C++ is choosing correctness over speed, and you have the ability to change that if you want. If you didn't want to have the destructor called automatically, how do you do that in C++ already? You knew it, and you have to call delete it manually. And so in the future, you can GC new it, and you can either wait for a delete or let the finalizer catch it. So here we say is that every type has a destructor, and every type has a finalizer. And so in a lot of ways, a destructor can be, do nothing, as most destructors do if you don't write one yourself. But the destructor really, its responsibility is to call the destructors of the base class and call the destructors of the things that are embedded. The other thing that a destructor will do is that if you GC new an object, so it's a garbage collected instance, the destructor will remove that object from finalization. So you can avoid the finalization pressure of creating a lot of these kinds of objects and actually help the stability of your system. We see that long-running processes that have a lot of finalization, it tends to hurt them in the end because they're waiting for memory to show up, and they might be running in low memory environments. And so actually building off of this practice, destructors are still a really good way of programming, even if you're working in a garbage collected environment. And what this gives you is that garbage collections just gives you the memory safety. You're going to avoid having these, because you're working with handles that have a narrower algebra than pointers, it gives you the ability to say, I'm working with type safety, and I'm reading code that makes sense, and I'm not going to accidentally leave a pointer dangling or anything like that. And every type also has a finalizer. So go back to all the code that you wrote 15 years ago, that class, it has a finalizer. The compiler generated it for you. Didn't know it, but it did. And that finalizer's responsibility is pretty much to do nothing unless you actually write code into it. So a finalizer is non-deterministic as far as you're trying to free up embedded reference classes or anything else. The responsibility of a finalizer is late cleanup. I really don't know when I'm going to clean up, so just clean up something that's essential. And that's expected, as you would see. Now, finalizer is just written with the bang character. You can actually call a finalizer explicitly using bang, just as you can call a destructor explicitly. And that helps you, write code that you would expect. Finalizers and destructors work together. There are a lot of things that you can do with this pattern, but because the compiler is doing all of this automatically for you, it's actually pretty simple to do. So here's an example written in C++ of how you make use of this kind of API. Message queue is something that you definitely want to clean up. It's something that has dispose. So it's a reference class, and all I have to do is declare it as if I want lexical scoping. So I kind of treat it's on the stack. And with this, I just have to make use of the APIs just as I would expect. Because it's on the stack, I use dot to access members. If it were on either the garbage collected heap or the native heap, I would use arrow, as I would expect. And because it's on the stack, it's guaranteed not to be finalized. Its destructor will be called, and that's guaranteed. If I had to write the same code in another favorite language, you really have to add a bunch of code blocks. So using and declare it the same way. And typically you have to write quite a bit more code in this way. And it kind of obscures the notion. What would happen if I forgot to write using for one of these? Then I would have missed calling the destructor. Its finalizer would have to clean up, and so I add instability to the system. So, again, if I were to write it out as a try block, I still have to write a block. Really have to remember that. And these are just things that C++ developers know how to do already. It makes sense to just allocate it on the stack if I want it to be cleaned up and be exception safe and all of this. And so writing extra blocks just doesn't make sense, and that's why we've done what we've done. So that's, deterministic finalization seems like, a long-awaited thing, but really it's very simple. It's already what you know, and we're just making sure that you can use that going forward. So generics and templates. You'll see this is generics cross templates. Quite often I've had a few people come up and say, generics, that's a great feature. It's templates done right. And really sad to hear that, because that person had no idea what templates were. Templates have become a radical movement in C++. It's just incredible what they offer, because an entire programming paradigm has been built up around them. Generics solve a problem very well. They create collection classes that are instantiated at runtime, and they solve type identity and a number of other things. But they certainly don't offer the power of templates. Generics have a compile time. They don't have compile time enforcement in the sense that you have to subclass the type parameters so that you have constraints. I have to make sure that it implements this interface. Templates, it really was a value constraint system where if it had that method, it would compile, and if it didn't, it wouldn't compile. So templates really are just as type safe as they ever always have been. But the cool thing about this is that C++ is supporting both generics and templates. And so that's the key thing to remember, that templates and generics aren't the same. We're doing both. And really the cool thing about this is that generics and templates work together really well in a lot of very cool situations. So templates are compile time enforced. They allow specialization, so I can create different kinds of collection classes for different type elements. And generics don't specialize, but they have a lot of other very cool things in that they're cross-language. I can use a generic from C#. So one of the cool things that you can do as a programming practice is take an existing programming pattern that you all know, the factory pattern, create a generic interface, create a template instance that is specialized for a class, and pass it out through that interface. And so you're using specialized code that's highly performant because it was written in C++, and let other languages make use of it through that generic. And very cool thing. But the other thing, too, is that via this kind of programming pattern and the combination of these features, is that all of those programming practices that were already there for C++, like using expression templates and modern C++ programming practices, they still work, and they work on the CLR. And so what you'll see is that STL practices of splitting algorithms from the actual implementation of a class are still valid things that you can do in verifiable code and make use of in your existing programs. So just how is a generic declared? In a lot of ways, they look and run like a template. So take the template keyword and put generic there, and you're well on your way to writing a real generic. So you can declare your constraints for it by writing where and followed by the types that it implements. And then those types you declare within the class, and you can make use of it. So going forward, if this was destructible, I would make sure that T is, even though it was allocated on the stack, it goes out and gets cleaned up. So even within generics, you're writing type-safe C++ useful code. The other thing is that generics and templates really do serve similar features. And so can I take a generic and use that to satisfy a template parameter? And the answer is absolutely yes, you can. And going forward, pretty much everything that you would expect to work, it's our goal to make to work. And that's really the message. So we're also making sure that STL works really well on the CLR. And to that end, we're implementing a version of STL that you saw in Eric Rudder's talk this morning, called STL.net. And this is a fully verifiable implementation of STL. You can take any kind of reference class and put it into that collection, and I can create an STL .NET vector, pass it off to another language, and it'll see it as an iList or any of the similar generic interfaces. But it's verifiable, but it demonstrates key programming practices of C++. I'm splitting the implementation from the actual algorithms that work on it. And so I can make use of all of the actual algorithms that I've written and just use them with this. It's actually a very minimal transition to go from standard STL to STL.net. The programming practice is so similar that it's very close. It's hardly anywhere. But you'll see that the different for eaches that we have, we're implementing for each in the language in the C# style so that you can make use of the different enumerators in the frameworks. And this really is because we've had so many people knocking at our door to do it, because it's just really easy to write code. And so that for each we wanted to make as general as possible, so it also works on STL. And so you can still use the C++ for each and create different function objects to pass on to and use that as an iteration thing. But you can see the code that's written here that I can make use of all of the existing C++ practices, including creating lambda expressions from Boost and other existing community practices. It just works as you would expect. And the cool thing about it is that this code is also pretty much verifiable. And that's great because when you're trying to take it into the partial trust space, that's really necessary. So the last thing that I'm presenting is one of the really cool approaches. One of the, managing lifetimes, that's really the difficult part of programming these days. And when you're dealing with the CLR, you're having to manage the lifetime of an object that's on the GC heap and an object on the native heap. And you're trying to coordinate the lifetimes of those. And a lot of the code that goes into that is actually quite boilerplate code. And not only that, it's really hard to write that code. There's a lot of it, and really we think that you shouldn't have to do any of it. So the compiler can do this. And what I'm showing here is a pretty easy thing. I want to take an existing class that in my program, it could be a 10-year-old MFC program or something else, a command line program. I want to make use of this new feature in the frameworks. And so you'll see this all over. As WinFX comes up, there are going to be a lot of very cool features that you're going to want to make use of in your existing code. And so all you want to do is put in your code something, an XML document, and in this case, you're saying that you're managing the lifetime. That should actually be embedded instead of a pointer. But the other thing is, I can start using that by taking, std string, and I say I really want to change that to a string as, a system string. And so we're introducing these new Marshall templates, and I think the cool thing about this is marshalling templates allow you to just say, I want to go from here to there. There are a lot of ways to go from here to there. And when you do that, in the past, you have to go through the documentation. How do I change a string to a char star so that I can pass it to my ANSI? And if you asked a question like that, how do I do this? You'd often get at least 5 different answers, and 4.5 of them would be wrong. So what we're doing is just saying, templates solve this problem. you have a way to go from here to there, and that's as simple as you want. You just say Marshall as, I want to get a string hat out of that, and you pass some expression. As long as that the Marshall template using overloading can figure out how to do that, it'll do it for you. And if it didn't know how to do it, either there's no way to do that, or you can just extend it yourself by adding it. So it's completely extensible. It just shows you the ability to solve problems in libraries. And as you'll see going forward, the libraries that we support, like STL.net and the marshalling library, it just solves a lot of these problems that you have going. And I think it just demonstrates that libraries are really a better solution for a lot of things. You'll see this too as lock is something that we're not introducing to the language because you can do it just as efficiently in a library and actually give the user more power and control over it. So another thing is actually taking a ref class and putting it as a template parameter for even a function. It just works, makes sense. And as I mentioned before, we're allowing any type to be templated. It's one of those fundamental things that templates are a compile time abstraction that really makes sense for users. Great thing to make sure that it just works everywhere the same way and you get the thing out of it. So another thing that's definitely interesting is embedding, you'll see here, taking a native class and embedding it in a reference class. And so this is even more problematic than the last one because I actually do have to manage the lifetime of that embedding the vector. So this vector is actually not embedded, it's a pointer. I believe it should be embedded in the example, but it can actually be embedded because the vector is requiring a stable list pointer that can't move around. And if it were on the GC heap, it wouldn't work. But rest assured, it works. We're making it work, and I think the next slide will show you how that works. And you'll see that one of the very useful things about taking that is that I can create many different APIs that are useful from different aspects. I can have an add function that takes a system string, and that add function can be used from any CLS language. But I can also have an add function that would be useful to an existing API. So if you're trying to build code that goes into the middle between an existing code base and some great new library that you're creating, you can actually build very useful APIs that way. So let me explain what currently is going on. This is code from that Quake demo that you saw at the very beginning. And what we're doing is saying that we're trying to manage the STL vector and hold on to it from a garbage collected class. And so what we see about this code is that we have to make sure that the constructor and the destructor of actually the finalizer for this GC class, and this is written in the managed extension syntax, have to manage that lifetime of the vector. And because it doesn't have any destructor, it's really not great code. It's not reliable. But a lot of this, creating that vector and deleting it, that's stuff the compiler can do. And so if we try to do even more, where I try to, say, inherit from a native class, so a great example is I want to take a native class that's existing code and just wrap it, make it look like it's a reference class that any language can make use of. And today that wrapping process is very tedious. You just have to write a lot of code that's kind of verbatim. So in this example, we're just simulating inheritance by taking the foo and bar functions that are in the native class and just repeating that API and directing that off. And so we think that's not the right way to write code. And going forward, this is what we've called the unified type system. So you might see this as unification. You've already seen part of this in that a hat can apply to any type and a pointer can be applied to any type. I can put any type on the stack. This is just kind of make everything uniform. And the unified type system, the full experience is that I can take any type and embed it in any other class. And what this gives you is every object's lifetime is pretty much uniform, only dependent on the type. When I instantiate it, is it garbage collected? All of its member instances are also garbage collected, and the compiler does a lot of the lifetime management, takes the tedium out of the code that's already written. And so this is actually what we've been calling mixed types. A pure type is one that a reference class that only inherits from other reference classes or only embeds or other reference classes, and pure type is also a native class that only inherits from a native class or embeds a native class. When a reference class or embeds a native class or a native class embeds a reference class, you're combining two different things that have different lifetimes. And so we're calling that a mixed type. And so you'll see that at the first one, ref is a class that inherits from two native classes and contains a native class, and vice versa for the other one. A native class that implements an interface, that's very useful. I just want to take my MFC class and implement this serialization interface and get the CLR to take care of all that useful things. And that just works for you. So this is how we're doing that. Let me step through the picture because it's certainly worth explaining. The native, you'll see that ref class M here is implementing two interfaces and inheriting from two native classes. And so that by itself makes it a mixed class. But it also contains a managed, a string that's a system string, and it embeds a native type, a std string. And so the std strings and the base classes N1 and N2 have a lifetime that needs to be static. It's on the native heap. It can't move around. And so obviously the thing is put that part on the native heap. The other things like the system string hat and the interfaces definitely need to be on the garbage collected heap so that the CLR can follow things around, follow the garbage collection, and make sure that if that's not held onto, the system string is itself garbage collected correctly. And so you split those two parts up. And to help facilitate identity, the managed part and the native part have references to each other, so it can always go back and forth. And so depending on how I want to create the pointer to it, to manage it, say I explicitly want to manage that lifetime by newing it, or create a handle to it by GC newing it. Either way, I can get to this type and make use of it, and it pretty much makes sense. So this is a very under-the-covers thing, and you would never have to see it. The compiler does all of that work for you. But the thing is that it's actually much faster this way, and because it's codifying an existing practice. And so you'll see that the code on the left is much shorter because the code is actually quite, it does a lot of things. So actually, I think I'm running out of time, so I'm going to speed it up. I'm actually pretty close to the end. A few other things that we're adding, parameterase, give you the ability to pass a number of arguments in a type-safe way, even more type-safe than var args. Both are supported. I mentioned operators are supported on handles. We're actually introducing XML documentation comments and delegating constructors. So very quickly, the very last thing we have is we're standardizing this. On October 1st, ECMA voted to create something called TG5, and it's a technical group to actually look at standardizing C++ to the CLI. And why are we doing this? Well, first, you're looking at this, we're changing the syntax of the language. You want to have some guarantee that we're not going to do that again. And so that's definitely the number one reason we're doing this. But it's also C++ loves community, and they like the standard they have now. And so we're just giving you what you want and a way to work with that. It's open. We've been working with a lot of partners. But the other thing is that WG21, the existing C++ committee, still matters to us. Herb Sutter, who was not here today, is at the WG21 meeting right now in Hawaii. And so it's just that commitment that we actually care about both of these standards and will still be involved in both of them. But even more, the people who are on WG21 are also involved in the ECMA TG5. And so who is involved in this? Tom Plum, which he's been involved in standards forever. And he's also been involved in the C# and CLI standardization. Rex Juschke, who wrote the C# spec, is involved. And pretty much everyone else that the who's who of C++ is involved. And so our plan is to have this standardized by the end of next year and then go through the ISO process and a year later have it standardized by ISO. So with that, you'll just see that we've got quite a few features on both sides. The key message that you get is that we want to use your existing code, and the great thing about C++ is it always has supported many paradigms, and we're just supporting them even more by using the cross-product of all of the existing technologies. So you get the two FAQs. Use .NET because, well, it's pretty cool, and use C++ because C++ programmers are the smartest guys around, and we just want you to come to us. So I'll be in the track lounge later today. I have a blog that I started that if you want to read, and pretty much anything else. But thanks again. I'll be at the Ask the Experts as well.